Let us start today's lecture. We are talking about the stress concentration factor, and in order to do so, we have gone through different equations, use of different equations. Actually, those equations are generated at the time of those equations are generated at the time of at the discussion of the bending of beams itself under three-dimensional condition. Now, let us go through, discuss the bending of the beams accordingly. Now, we know the stresses and deflections of the beams are a general in a general cross section subjected to bending. The causes having a general due to the stresses and seen and deflections of beams having a general cross section which is subjected to bending. When means a particular type of beam of particular cross sections, if it's engaged with external loads, we know as per our knowledge of the strength of material in third semester that is supposed to be bent and across along its length itself. Actually, the moments caused the bending are due to the lateral forces acting on the beam. We assume that different vertical forces of concentric in nature is acting over the surface of the beam. This is called lateral forces, and which is normal to the longitudinal axis of the beam itself. This lateral forces is addition to causing bending and fractal stresses in transverse section of the beam, and also introduce shear stresses. So what we have seen, due to the action of the beam, due to the action of this external lateral forces, which is normal to the axis of the beam, is trying to bend the beam, and beam is also resisting its bend as per our Hooke's law. It is applicable. This theory is applicable so long Hooke's law comes into force. Means force if the loads are removed, the concerned member will go back to the original shape. Means this bending is elastic in nature. So what we have seen that this due to the lateral forces, we have seen across the different section, the bending moments are generated, and these bending moments are created flexural stresses in transverse section. These bending moments are generated flexural stresses in transverse direction itself. Now, it's also, you have witnessed that it's also created shear stresses, but generally the transverse forces, transverse longitudinal tensile or compressive forces are the predominant forces. And in cases in certain application, they are also introduced the shear forces across the beam due to the application of the external loads and of particular nature of the external load and a particular orientation of the load itself. Now, what happens? The bending stresses are normal to the section. The bending stresses, flexural stresses are generally normal to this section. We see this is a section, more or less triangular in shape. This section is more or less triangular in shape in the closest approximation, and the flexural stresses are the effect of the transverse shear forces are discussed. We'll discuss afterwards. Now, due to the pure bending moments, only normal stresses are induced here. And you are thinking that there is no shear stresses, but afterwards we will discuss it. But we are thinking only bending moments are acting over the stress itself, acting over this beam itself, and this creates a normal stress which are normal to the sections are introduced due to the action of this bending process itself. Now, generally, so far we have discussed only beams having an axis of symmetry are considered, but here it is an initial straight beam having a vertical section of symmetry and subjected to a bending moment acting to this plane of symmetry. So what we have, it have a vertical section of symmetry this particular bending moment has a vertical section of symmetry and subject to the bending moment acting in this plane of symmetry itself. So what is exactly meant by the symmetry is we should imagine a straight line or or a plane across a particular section, and this section will be such that these are equally extended in both sides of this straight line or in both sides of this I mean the plane itself. Only then this is called symmetry. Also that if it's one side of the plane, one side of this concerned beam will be exactly a mirror of the other side of the construction beam with the along the axis of symmetry or plane of symmetry itself. Now, here, what is we subject with this? We assume that a bending moment is acting along this plane of symmetry. This is more or less a symmetrical plane, and we have a three-dimensional axis of rotation here. Three-dimensional axis, not rotation. That is x-axis, y-axis, and z-axis, and this is going through the centroid of the beam itself. And this beam is exactly symmetrical against a plane which is going through the centroid of this beam itself. Now, here we assume this plane of beam symmetry is along this xy plane. This is along the xy plane. This is the plane of symmetry itself. Now, and the bending moment actually acts in this xy plane. Means if we extend this from here to here, this total beam will be subjected to a bending moment like this along this xy plane itself, which will act in a xy plane itself. Now, we here always assume that the planes remain same before the bending takes place, and it after before the bending takes place and after the bending takes place. Though the flexural stress which we are telling just at this moment, the stress induced due to this elementary bending moment. And we know from the strength of material equations of strength of material, this sigma x, the flexural stresses, is equal to sigma z, mz multiplied by y divided by ij. What is mz and what is y and ij? We are supposed to know. The origin of the coordinates is here in the centroid. Okay, and this z axis is coincides with the neutral axis itself. Z axis itself coincides with the neutral axis. So this is the z axis. It is coincides means neutral axis is either acting along this particular plane itself. So what we have known, what is neutral axis is the axis or a plane. We can think of a plane here, which is going through here and here, through which a plane acts. From here to here, we can imagine a plane, and we assume that this plane, that these elements of acting over this plane does not face any sort of stresses of strain, compressive and tensile in nature. According to the action of the stresses, this beam can be bent downwards or can be bent upwards itself, causing bending flexural stresses over the top portion and at the bottom portion of the beam. And with the neutral stresses or neutral axis, if we consider an axis through the CG, that will be a neutral axis which comes here, which will have to not face any sort of flexural stresses itself. And all the all these rings of, all these structures or all these strings of the beam over the stress over the neutral plane will experience a compressive stress, and that below that stress is the tensile stress, and maximum will be at the top forces and minimum will be at the bottom surface. And maximum compressive will be at the top and maximum tensile will be at the bottom surface itself. Now, what is so? The origin of the coordinates, origin of the coordinates coincides with the center of the cross section itself, and Z coincides with the neutral axis. What we are telling you just on the moment, Z axis coincides with the neutral axis. It is the Z axis shown here, and we know the Z axis is perpendicular to the XY plane itself. So, and our plane of bending is along the XY plane itself. And thus we can see from a neutral axis will go pass through the Z-axis itself if we only consider a section of the side of the beam, where neutral axis will be represented by a straight line here, which is given by the neutral plane. And this neutral axis here will be along the Z-axis or coincides with the Z-axis itself. Now, here we are having a minus sign here. This minus sign will take the care of the sign of the stress itself. A positive bending moment, as shown here, it produces a compressive stress at a point within the positive y coordinates. Means positive bending moment will cause a compressive stress. So this is the positive direction of y-axis. So a positive bending moment will